For decades, time travel has been dismissed as impossible. But this physicist just cracked the code using quantum mechanics. He's trying to prove that time loops might actually exist without breaking reality. So could this be the first real step toward building a time machine? In everyday life, we're used to time moving forward in a straight line. It goes from the past to the present to the future. That's how people saw it before Einstein, because that's how it feels to us. But when Einstein showed up, he told a very different story. He showed that both space and time are woven together like some flexible fabric into one thing called space-time. Space itself can bend and twist, and time does the same with it. The fabric of space-time bends and gets curvy when we place heavy objects in it, like planets, stars, or black holes. The heavier the object, the more it will get stretched and bent, slowing down time around it. Movies like Interstellar showed it pretty well, even though the characters only spend a few hours on the planet. When they return to the spaceship, 23 years have passed for the astronaut waiting there. Why? Because the black hole's extreme gravity warps this fabric of space-time itself, and the closer you are to it, the slower things go for you. Sounds insane, but that's how our universe works. And that's not just black holes. All massive objects, like the sun, for example, bend the fabric of space-time around them. This is also why planets orbit in curves. All this gave physicists a pause. If we can bend space-time, can we bend it to such a way that we'll make a loop out of it? It would be like going on a journey that bends back on itself, meaning that if you followed it, it could return to the past and experience the same moments again. That would be pretty insane. Imagine that you walk down a hallway expecting to exit through the door at the end, but instead of a door, you find yourself standing right back where you started, walking into your past. But just imagine how hard something like that would be to pull off. Yes, heavy objects can stretch and twist space-time, but even those massive things still don't loop time. They just slow it down very strongly. It's hypothetically possible, but it would require super extreme conditions. For example, if the black hole gets a little extra boost, spinning, it could theoretically bend space-time around it into a loop. There are also some wacky ideas, like exotic matter and wormholes, but they're all speculative. But let's assume that there is a way to make a CTC. Creating it isn't our only problem. This is where the paradoxes begin. If a time loop could exist, wouldn't it create contradictions? The grandfather paradox is just one example. If you follow a big loop like that and accidentally prevent your grandfather from meeting your grandmother, you'll make it mean that one of your parents is never born, and you weren't born either. So how could you travel back in time in the first place? Or what happens to you after that? There are other ideas like that, like destroying your time machine before you use it, or giving William Shakespeare his own plays. There are infinite possible paradoxes. All this is happening because of entropy. It's one of the main laws of physics, this idea that chaos in the universe always increases. Things start as something normal and structured, but eventually they break apart, becoming weird and chaotic, and can never go back. Ice melts but never refreezes into its original shape on its own. Our bodies age instead of getting younger. We remember the past but not the future. All these are examples of entropy. So, like, if time travel were possible, how would entropy behave? Would a broken glass fix itself? People would grow younger, and people would lose their memories? That's exactly how paradoxes like grandfather's paradox are born. Well, this is where the recent theory changes everything. The physicist Lorenzo Gavassino has a cool idea to explain this issue. He tackled quantum mumbo-jumbo, working with something called quantum fluctuations. See, the universe is never completely still. Even in empty space, at the tiniest level possible, there are constant random changes in energy. These are those quantum fluctuations. They're like tiny, unpredictable jitters that pop in and out of existence. Yeah, Our universe is just weird like that. It's like a lake. On a normal scale, it looks smooth, but if you zoom in super close, you'll see tiny, unpredictable ripples forming and disappearing all the time. Our universe is the same with quantum fluctuations. These fluctuations happen everywhere, and they become really important when dealing with stuff like black holes and time loops. Now, back to the time loops. Gavasino says that in a time loop, quantum fluctuations mess with entropy in a strange way. Ideally, the chaos should increase. As usual, we're getting older, our spacesuit is getting weary, broken things don't fix themselves, and so on. But it seems like instead of always increasing, chaos in a time loop can randomly decrease. This means things that should be irreversible, like aging or breaking something, could actually reverse themselves. So yep, if you try doing something wild during time travel, it won't really work. If you try to prevent your grandpa from becoming your grandpa, the universe could reverse that change, making it like it never happened. If you travel to the past, your memories could vanish, meaning you wouldn't remember the future you came from. And if you try to break causality, the universe might just remove the contradiction. Time would always find a way to correct itself, preventing paradoxes. Scientists actually suspected this for a while now. Many of them have believed that if time travel were possible, the universe would somehow prevent weird paradoxes. Basically, it would make sure that everything that happens must be logically consistent with itself. Well, Gavasino's work basically gave a mathematical proof of that using quantum mechanics. Of course, there was another wild theory, the one with multiple universes. You definitely saw this in the movies. It says that when we travel back in time and change something, we simply create a new timeline. The old one remains, but this one would go a completely different way. But this idea is more about cool sci-fi than actual math and physics. But does that mean that time travel actually exists? Well, not right now. Even if time loops could exist in theory, that doesn't mean they actually do exist in real life. Stephen Hawking, for example, thought that these time loops are impossible. He said that the universe works in such a way that it would simply prevent time loops from forming. He even organized his famous time traveler party. Unfortunately, no one showed up. But many physicists still believe time travel is impossible, at least on a macroscopic scale. They even kind of managed to do that. For example, teams from Oxford and Vienna wanted to see if they can reverse one single electron back in time. And they managed to do that inside of a quantum computer, though the effect was tiny, only a fraction of a second. Recreating that normally would be absolutely insane. If we wanted to see something like this naturally, we would have to observe 10 billion electrons per second for the entire age of the universe. And even then, we'd only see it once. The more particles they tried to rewind, the more errors appeared. With one tiny electron, it worked well. But when they got to 3, accuracy dropped in half. But even if we never find a way to travel through time, understanding all these things could still help us a lot. It would help us study black holes, the early universe, and even quantum technology. So, while time machines are still science fiction, this research is pushing us closer to understanding our universe. It looks like there's a terrifying crack in our understanding of the universe. Scientists have compared how fast the universe expands. 2 methods, 2 measurements, completely different answers, and no one knows why. As they dive deeper into this, a new terrifying idea came up. Our entire universe might be spinning. If that's true, it changes everything we know about space, time, and even how the world will end. To understand what's going on, let's talk about how our universe expands. How exactly is it expanding? Into what? We first noticed this about 100 years ago. For many years, people thought the universe was eternal and unchanging. Then came Edwin Hubble. He observed the universe in the telescope and realized the light that came to our planet was coming from galaxies that were moving farther away from us. The galaxies weren't sitting still. The whole universe was moving. And this became one of the most revolutionary discoveries in history. The movement started with the Big Bang. It happened about 13.8 billion years ago. The entire universe, all matter, energy, space, and time burst forth from an incredibly hot, dense point. The bang sent a shockwave, giving all the things and particles their initial boost. That's how they started drifting away from each other. The thing is, they weren't drifting away into open space. No, they created space themselves by drifting. Let's say you're holding a balloon. You draw some dots on it. You start blowing air into it. The balloon gets bigger and bigger. And every dot on its surface moves away from every other dot as the balloon expands. As dots move apart, they basically create space between them by moving away from each other. So the universe isn't expanding into some mysterious space. Space itself exists only within our universe, born between moving dots. The Big Bang boost was so strong that the universe started expanding incredibly fast. It's hard to even imagine. If you were chilling and watching this from the side, it would seem like the entire universe appeared out of nowhere in less than a moment. You wouldn't even hear it because there's no sound in vacuum. There would be nothing. Then you would just blink and bam! The world is everywhere. That bang was so huge that the universe is still expanding from it even now. Even billions of years later, it's space itself that's stretching, with every point on it drifting farther and farther away, including us. We're just moving at a more gentle pace, sort of. So when we figured out everything was expanding, the next question was, how fast? Turns out the movement speed is different for different galaxies. We noticed that the closer things are to us, the slower they drift away from us. And the farther a galaxy is from us, the faster it appears to be moving away. And they're moving constantly. We say, for example, this galaxy is 100 megaparsecs away. But since the galaxies don't actually stay in one place, that means this galaxy is moving at a speed about 4,300 miles per second away from us. If the distance doubles, then the galaxy's speed doubles. So, for example, if a galaxy is 1,000,000 light-years away, it will move away from us at a speed of about 46,000 miles per hour. 2,000,000 light-years away? Double it. Now it's about 92,000 miles per hour. 10 million light-years away? Almost 500,000 miles per hour. Scientists call it Hubble's law. Speed is equal to Hubble constant multiplied by distance, and the Hubble constant is the exact magical speed number that we keep adding up every time we move 1,000,000 light-years farther. So, the Hubble constant is basically the rate at which expansion happens. But there was a problem. A problem that seemed tiny at first, but it was actually hiding a huge disaster. When we measured Hubble constant using two different methods, for some reason, we got different results. The first method was to calculate it based on what we see around us right now, today. Different stars, galaxies, their light and brightness. In certain stars, brightness changes in predictable ways. Huge star booms, like supernovas, act like cosmic lighthouses. We know how bright they should be, and thanks to that, we can calculate their distance and speed. It's all clear and simple. But then, scientists tried something totally different. They often used this trick. To figure out how the early universe behaved and then simulate everything from the start, it's like creating your basic characters in Sims and letting them do whatever, hoping that they'll do things in predictable ways and not pull off something wild. We can guess what the early universe looked like because we can still detect the faint afterglow of the Big Bang. We have ultra-precise telescopes that allow us to find an ancient, very first light and very first traces of energy that were born in our world. This post-Big Bang afterglow is literally filling up the entire universe. It's just scattered around like some dinosaur fossils. So we take these fossils and recreate the entire dinosaur based on them. And when we measured what the Hubble constant should logically be, based on how our universe was starting, we got a different number. It doesn't sound like a big deal at first. Based on what we see today, every 3 million light-years away, things are moving about 40 miles per second faster. But based on how our universe was supposed to develop, the number is about 45 miles per second. Literally just 4 miles or so, right? But in cosmology, it's an ultimate red flag. The error bars have shrunk so much that now this isn't just a meh, probably fine situation. It's a literal tension in measurement. And that's exactly what scientists call it, the Hubble tension. It's a serious difference between two super precise measurements based on very different methods, and both of them seem equally right. Imagine using two ultra-precise clocks to check how fast an athlete runs a distance. And in the end, one of the clocks says 10 seconds, while the other says 11. What in the world does that mean? That's terrifying. The two numbers should match, and since they don't, one of three things must be true. First, maybe one of the measurements is wrong, which is very unlikely because both methods are super reliable. Second, maybe something in our interpretation is wrong, but that's also unlikely, since many scientists get the same result and agree that the tension is a real deal. And finally, the scariest option? Our entire model of the universe is missing something. That's why scientists are freaking out, and as it turns out, they had a reason to. Recently, a new research team from Hawaii proposed something wild. What if the universe is very slowly rotating? If that's the case, it would be absolutely insane. Here's why. First, if the universe actually rotates, even super slowly, it would mean that the laws of physics might be slightly different depending on where you are or which way you look. That breaks one of our most sacred ideas about physics, that space is the same in all directions. Second, it could mean we've misunderstood the entire cosmic history. Maybe we don't actually know how fast the universe is expanding when it was born, or what dark energy is. That would be a huge disaster. And finally, the most horrifying of all, if it's spinning, then it must spin around something, right? If there's a cosmic axis or rotation, it might suggest a preferred direction. It would be something like cosmic north. We thought there's no special place in the universe, but we might have been wrong. Maybe there's a special place after all. It's like finding out the reality itself has been tilted a tiny bit the whole time, and we just noticed. Right now, we're in an exciting and scary place. Either we'll discover new physics and maybe something about dark energy, or we'll find a subtle error in one of the measurements. Or who knows, maybe something totally unexpected will show up. In any case, solving the Hubble tension could revolutionize our understanding of the universe's origin, structure, and our place in it.
Inside a chunk of diamond smaller than your fingernail, scientists have just discovered something that shouldn't exist. Not just a new material, a new phase of matter, and it breaks the very rules of time itself. The biggest problem is no one fully understands how it works yet, not even the people who made it. So let's take a peek and try to figure it out. The story started over a decade ago. Scientists created the first time crystal. Sounds like some mysterious component for a time machine, but it's something even weirder. Take a regular crystal and check it out under a microscope. Like everything around us, it consists of molecules and atoms. What makes crystals special is that their atoms are arranged in a repeating pattern. A salt crystal, for example. If we look at it, we'll see a repeating pattern inside it. And this pattern is the same everywhere, no matter how large or small the piece of salt is, or what shape it is. In the whole crystal, it's unchanged, and it will remain the same no matter how much time has passed. You might also know that all the atoms around us are constantly moving, even at very, very low temperatures when everything freezes and nothing can stop them. Their movement is random, chaotic, and unpredictable. They're just jiggling in space. But time crystals have their own special quirk. Not only are their atoms arranged in the same pattern just like regular crystals, But these atoms also moved in a looped, endlessly repeating dance. It's super weird. The atoms in time crystals are like an endless dance party. All the guests repeat the same moves in the same order over and over again. The movements in these dances can be basic and simple, or overly complex and chaotic, but they're always looped in time, hence the name. Now, just to clarify, these crystals aren't the kind we're used to. They don't look like gems, diamonds, emeralds, or anything like that. Actually, they don't look like much at all. The beautiful name time crystal describes a new, very strange kind of matter that changes in quantum states, which is what we call the weirdly looped dancing atoms. But even after scientists discovered them, there was something even crazier about them. These dance movements, for some reason, persist even at absolute zero temperature. In all normal materials and objects, if we cool atoms down to such a crazy degree, they would freeze, lose energy, and stop moving. In time crystals, they continue their endless dance as if nothing happened. Oh, and that was only the beginning. Scientists also got stunned because the existence of time crystals seemed to violate the second law of thermodynamics. Now, this law states that over time, any system becomes random and distorted. For example, a warm coffee will distribute its heat and become cold. Ice dropped in the water will eventually melt and unite with it, making water colder, and so on. At first, they thought that time crystals broke this law because it seemed like their atoms can move indefinitely, like a perpetual motion machine. It seemed like not only do they move constantly in the same pattern, no matter what happens to them, but they don't need any energy to do so. But then it turned out that they do require energy after all, either from lasers or magnetic fields. So even though they're little marvels, they don't break our physics laws. Yet. There were theories that this stuff could exist. Time crystals were first predicted in 2012 by a theoretical physicist, Frank Wilczek. Not all physicists accepted the theory at the time. Many believed that the crystals would violate the second law of thermodynamics, which means breaking physics. But the universe really doesn't care what scientists think, and Frank Wilczek won a Nobel Prize for one of his works. Still, some scientists were skeptical about this until time crystals were invented for the first time in 2016. Research from the University of Maryland managed to create one. They did it like this. First, they took a regular crystal and cooled down the atoms inside it to near absolute zero, almost stopping them. Then they started shocking these atoms with lasers. It made the atoms switch between different states repeatedly without absorbing any energy from the laser. You could say that the laser gave them a beat and made them dance by themselves without anyone's help. The result was the first time crystal ever. This was an amazing breakthrough, and ever since then, physicists kept studying time crystals to see what else these guys could do. The biggest problem was that such perpetual motion only truly exists forever in ideal time crystals. And since the time crystals in our experiments weren't ideal, they lasted only a few minutes before they melted and started behaving like regular matter again. But that didn't stop scientists. They wanted to make time crystals stable and usable. In 2021, they made another breakthrough. Researchers at Google collaborated with a bunch of big universities and used Google's quantum computer to create a much bigger and much more stable time crystal. If we manage to implement this property, these crystals could help us get closer to full-fledged, usable quantum computers. One of the biggest problems for this technology was memory. But the loop dances in time crystals might help us store information on a quantum level. That would be absolutely insane. Now, another thing scientists aimed at was a new kind of ultra-precise clock. Time crystals could also help us with that. And now, in 2025, they finally achieved big new successes. They took time crystals even further and created a time quasi-crystal. It's like the jazz version of a time crystal, more complex, a bit more chaotic, yet still coherent and weirdly beautiful. A team led by the researcher Chong Zhu created an atoms dance that was based on the golden ratio, the same perfect number we see in nature in seashell spirals and sunflowers. In most time crystals, atoms dance to a simple beat like tick-tock, tick-tock. In time quasi-crystals, they gave these guys a melody in Phrygian scale over a Fibonacci timed beat. In simple words, their movements became complex, not looping anymore, yet it still feels like actual structured dance, not random noise. Like a mosaic where no tiles repeat exactly, but still form a wonderful pattern. They started with a tiny chunk of diamond. Then they started hitting it with high-energy nitrogen atoms, knocking some of the diamond's carbon atoms out of place. That left behind empty pockets. Electrons rushed in to fill them, creating little quantum systems inside the diamond. Each of these pockets was highly microscopic, and the final system had over 1 million of them interacting together. Then came the microwaves. Using the magic of 2 overlapping pulses and golden ratio, they stirred the quantum particles into this bizarre, orderly, not looped time rhythm. And just like that, the time quasi-crystal was born. What they got was a stable, non-repeating atomic rhythm in time, something that, mathematically speaking, shouldn't be possible. And it's an entirely new phase of matter. So this isn't just a cool physics trick. It's a doorway into a part of the quantum world we barely understand. Normally, when you pump energy into a system, it either settles into a pattern or falls apart in chaos. But this one did neither. It found a new kind of order. But more than that, it might unlock technologies we haven't even dreamed of yet. Quantum systems like this could be shockingly stable, which is gold for quantum computers. Finally, quantum memory is on the horizon. Quantum computers could use these time quasi-crystals to store data long-term. Next, quantum sensors could use their incredible sensitivity to detect even the tiniest changes in the environment. And finally, the ultra clock we mentioned before, it's coming too. These crystals would help timekeeping devices be ultra-precise. Of course, we don't need this in daily life, but it will be incredibly useful in science. Strangely enough, it turns out that the same fragility that made these crystals difficult to handle also made them perfectly tuned detectors. All this is theory for now, but as scientists continue to study this, some usable tech might not be far behind. Guess what? The universe can get actual scars, just like when you fall off a bike. Well, here's why. Before the Big Bang, the universe was extremely hot, dense, and full of energy, and it seemed like everything was going well, until that all changed about 13.8 billion years ago. Then the universe exploded. After the blast, it expanded incredibly quickly. Our human brain can't even perceive how fast that expansion was. Sometime later, the universe started cooling down. As it did, giant, terrifying scars cutting through space-time appeared all over the place. And if we study these scars well, we can even get insight into time travel. These days, we call these scars cosmic strings. They're like stretch marks that appear when the skin expands too quickly. Or we could also compare them to cracks that form in the ice when it freezes. These strings are likely very thin, about the size of a proton, a positively charged subatomic particle. Yes, subatomic means smaller than an atom. The strings are also extremely dense and can stretch for light years. Now, imagine these cosmic scars floating through space, not interacting much with their surroundings. When two cosmic strings pass each other, they could warp space-time in such a way that it creates a time machine. If you were to travel along a certain path around these strings, you would end up returning to your starting point at an earlier time, which is traveling back in time. Now, let's admit it, this idea sounds like something from science fiction, but it's supported by cosmic string theory, and the math behind it seems to work. Unfortunately, no one has observed cosmic strings yet, so for now, it's still a theory. In 1991, one physicist proposed an idea for how cosmic strings could enable time travel. If two infinite cosmic strings passed each other in parallel, they would warp space-time, creating a time loop. This loop would allow someone to travel back in time. Even better, this idea doesn't contradict Einstein's theory of general relativity. which suggests that large objects can bend space and time. These bends in space-time could allow a shortcut through time. His now well-known concept of closed time loops also helps explain how wormholes might work. So, a wormhole is basically a theoretical tunnel connecting one place in space to another. Some people believe that by using such tunnels, we could create shortcuts for incredibly long journeys through the universe, which would allow us to visit other star systems and galaxies. So, let's say you manage to create a wormhole and even accelerate one of its ends to near the speed of light, and then you send it back to where it came from. Well, at that moment, those two ends are not synced anymore. One is in the past, while the other is in the future. And if you somehow manage to walk between them, you'd be time traveling. You could do something similar by placing one end of the wormhole near a powerful gravitational field, like a black hole, and keeping the other side near a weaker gravitational force. This way, according to the theory of relativity, time would pass more slowly nearer to the strong gravity side, and it would allow a particle or another chunk of mass to remain in the past relative to the other side of the wormhole. At the same time, if you decided to create a wormhole, you'd have to keep in mind that they are super dangerous. They might collapse all of a sudden. They're likely to be highly radioactive, or you could come into contact with toxic exotic matter inside. But let's get back to the math behind the cosmic string time machine idea. Admittedly, it is solid, but it doesn't mean such a time machine is possible yet. To use this way of time travel, we'd need to reach near light speed, and it might be impossible. According to Einstein's relativity, the faster an object travels, the more energy it needs to continue speeding up. In other words, we don't yet have the technology or energy sources to accelerate a spacecraft to these speeds. The idea of two infinite cosmic strings is also questionable because we can't create something that's infinitely long. So, while this time travel model is mathematically sound, the infinite nature of the strings would make this exact model impractical. At the same time, some scientists still believe that cosmic strings are a better possibility than most other models, like wormholes. In any case, before we can start considering time travel, we need to discover cosmic strings. Luckily, there's a group of astronomers working to detect low-frequency gravitational waves by measuring signals from a type of star called a pulsar. Now, pulsars send out regular pulses of radio waves, and by measuring small changes in the timing of these pulses, scientists can detect subtle shifts in space-time. Those changes are caused by gravitational waves, which are ripples in space-time. Now, so far, we've only detected gravitational waves coming from black holes. But in 2020, there was one strange signal that didn't look like it came from black holes. It could be coming from cosmic strings. And here, we need to mention string theory. According to it, the universe is made up of more than just the four dimensions of space-time. There are additional dimensions that are hidden from us. Plus, the basic building blocks of the universe aren't particles, but tiny vibrating strings. These strings can vibrate at different frequencies to create different fundamental particles. These strings, from string theory, could have stretched out during the early universe and become the very cosmic strings we've discussed. In the coming years, we might get more information about them from a space-based gravitational wave telescope called LISA. It's supposed to launch in 2035. But if the signals picked up in 2020 really came from cosmic strings, it could mean a huge breakthrough in physics. In this case, string theory would become the right framework for understanding the universe. It would completely change the way we think about the building blocks of our reality. On the other hand, even if the signals don't turn out to be from cosmic strings, this discovery would still be important. It would give scientists more information on what cosmic string signals might look like in the future. And while we're not yet at the point of time travel, the discovery of cosmic strings could take us one step closer to understanding the mysteries of the universe and maybe even the possibility of traveling through time. Now, time travel is a popular theme in science fiction, but in fact, moving forward in time happens naturally. Right now, you are traveling into the future at a steady rate of 1 second per second. However, scientists have discovered that this rate can change depending on speed and gravity. Einstein's special theory of relativity explains that time slows down as an object moves faster. The closer you get to the speed of light, the more slowly time passes for you, compared to someone who isn't moving at all. The general theory of relativity adds another factor, gravity. The stronger the gravitational pull, the more slowly time moves. Near massive objects, such as the surface of a neutron star, black hole, or even Earth, time runs more slowly than it does far away from these space objects. If someone were to stay near the edge of a black hole, where gravity is incredibly strong, only a few hours might pass for them, while thousands of years would go by for people on Earth. If they returned, they would have effectively traveled into the future. This is a real and scientifically proven effect. A real-life example of time travel, though on a tiny scale, can be witnessed in space missions. For example, this cosmonaut spent a total of 748 days aboard the space station Mir during 3 separate missions. Because Mir was moving at high speeds relative to Earth, it experienced time dilation. As a result, he aged 0.02 of a second less than had he stayed on the ground. Now, this difference may seem tiny, but it shows that time moves differently depending on speed and location. But while traveling to the future is scientifically possible, traveling to the past is much more complicated and controversial, and leads to logical paradoxes. Imagine you throw a billiard ball into a time machine. It travels to the past and collides with its earlier self. This prevents the ball from ever entering the time machine in the first place. A contradiction.
You may have time traveled multiple times already. You just don't remember it. A recent study says that all your memories of the trip would be completely erased as soon as you're back in the present. And you can blame it on something called entropy. To explain it, we first need to talk about closed time-like curves, or CTC. This is a closed path where a particle could travel, and it ends up right back at its starting point, at the exact same time it left. In other words, it's like a cosmic time loop. Take this notebook paper. Picture each line as a different timeline with a beginning, a middle, and an end. Now, if you roll that sheet of paper, the lines connect. Suddenly, they form a continuous line with no beginning or end. That's what CTCs are, closed timelines that don't have a starting point. Past and present blend together in an eternal time loop. Now, a more practical example. You're taking a walk around a park. A woman jogs past you, and a dog starts barking. You keep walking, but then, wait a minute. You realize you're back at the exact spot where you started. The same woman jogs by, and the dog barks again. But here's the thing. It's not just that you've returned to the physical starting point of your walk. In a closed time-like curve, you're retracing not only your steps, but every single second of reality itself. Alright, now think about the big moments in your life. Being born, graduating from college, getting married. If all these events are part of one big time loop, that means time travel is possible. It sounds crazy, but there's a concept behind it called the self-consistency principle. It says that time travelers can't create time paradoxes. I mean, time travel can't just be this wild, chaotic mess like those crazy butterfly effect scenarios. Even if you go back in time, everything in your life still has to fit together in a way that makes sense and lines up with what we already know today. I'll explain. Let's say you go back in time and stop your mom from meeting your dad. But here's the problem. If they never meet, then you wouldn't exist. And if you don't exist, how could you have gotten into the time machine in the first place? That's a time paradox. That's why time travel could only work within these closed time-like curves. No matter what you do, the past, present, and future are locked in. They're always going to play out the same way, like a loop. Okay, so now you understand what CTCs are and why they're important for time travel to make sense. Now, we can finally talk about entropy and why it's probably the reason we'd lose our memory after a trip to the past. Entropy is a way to talk about disorder, chaos, or randomness in a system. Imagine a super clean, minimalist bedroom where everything is neatly arranged. Everything's in order. That's low entropy. But then, picture a messy teenager moving in. Every day, clothes, books, and random stuff gets scattered around the room. It's a mess. That's high entropy. In nature, things usually trend toward more disorder unless you actively work to keep them organized. Like this ice cube. It's made up of water molecules, all neatly lined up in perfect order. Low entropy. But if you take this ice cube out of the freezer, it will melt into water. See how the puddle looks messier now? In this form, the water molecules can be arranged in so many different ways. They're all disordered and random. And that's higher entropy. If we apply this idea to time travel within a CTC, the closed time loop, things get even more interesting. According to specialists, a key feature of this circular journey is that the level of entropy has to be the same at both the beginning and the end of the trip. Here's an example. You're just living your everyday life. Nothing too exciting going on, so the entropy level is low. But then, you get inside a time machine and go back to the past, right before you broke up with your high school sweetheart. By traveling through time, the chance of you changing the past and totally throwing your story into chaos is pretty high. Let's say you don't break up with her, and in this second chance, you decide to propose to her. See how everything could go totally sideways, right? So, when you go back to the past, the entropy is at a super high level. Now, you get to the exact moment when you're about to talk to your past love. At that point, entropy is at its peak. You're about to kneel down, show her the engagement ring, when, well, here comes the self-consistency principle, and it throws a cold bucket of water on this whole romantic idea. Remember, in a closed time-like curve, nothing can significantly change the present reality. All the changes a time traveler makes in the past can't cause any historical paradoxes. So, sorry to say, but you're not going to end up with her anyway. You decide to hop back into the time machine and return to the present. You get back into your routine, your job, and well, your single life. After completing the time loop, your timeline is back in order. Now, the level of entropy is low again, just like it was at the beginning of your journey. It's like you did a reset on the system. And that's the bad side effect of all this. Pressing this reset button would probably erase all your memories of the trip by the time you get back to the present time. Unlike in the movies, a time traveler probably won't recall anything. What? Now, answer in the comments. Even if you can't remember what you did after going back to the past, would you still take the risk? I'm guessing your answer would be, yeah, of course. That would be my answer too. After all, we could bring our phones and still make tons of cool photos on this trip, right? Well, no. This is where the laws of physics crush our hopes. Again. The second law of thermodynamics says that in an isolated system, entropy, or disorder, tends to increase over time. But this doesn't apply only to humans, but also to non-living things. It's why you can't unscramble an egg, unmix coffee from milk, or take your phone into a time machine. If a time traveler stores any data on their smartphone during their journey, experts believe it will probably get wiped out as soon as the trip ends. All the videos, photos, poof, gone. That's because machines probably wouldn't work properly when we go back in time. For example, let's say you bring a classic analog watch with you. For all the reasons we've already talked about, when you come back to the present, the clock needs to be exactly where it left off. I mean, the clock hands should be in exactly the same position at the beginning and the end of your journey. But to make that happen, it's likely that the frequency and number of ticks during the trip will be different. That could cause small problems in clocks made for regular time, making them unreliable. Something similar could happen with your phone. Its system probably wouldn't work as it should. All these consequences of time travel were described in a study by a mathematician published in 2024. While his theory doesn't determine whether time travel is actually possible, it does point out the strict conditions that would have to be met. And, well, it seems like having a time machine at home might not be as great as it sounds. In the end, you wouldn't remember a single thing about your amazing trip, and you'd probably just end up exactly where you are.
Time is nothing but a magician's trick. Or is it? We're used to time zipping along like a car, always pointing into the future. It creates cause and effect, lining events up one after another, like dominoes. Sometimes it stretches between moments, getting so slow it might even want to stop. And it's got a spotlight on right now, because that's the only moment that truly matters. But there's a new theory that it might not exist at all. We usually think of space as having three dimensions: up and down, left and right, forward and back. And everyone thought that time was a separate thing, just a universal clock ticking away in the background, and it's the same for everyone. But then Einstein came forward. He decided to surprise everyone back in 1905 when he introduced his special theory of relativity. It said that time is another dimension, just like the others, and they're all tied together in one big space-time. Based on this, it turned out that time can change depending on the speed at which you move. Now imagine that we take two twins. Twin A stays on Earth, Twin B takes a journey into space on a spaceship moving at a speed close to the speed of light, let's say 90% of that speed. Twin B travels to a distant star and then returns to Earth. For Twin B, it feels like the journey only took a few years. But when they come back to Earth, it turns out that Twin A has aged significantly more. They find out that 20, 30, or even more years have passed on Earth. That's all because of the phenomenon called time dilation. It happens when we're reaching speeds close to the speed of light, causing time to slow down for the traveler relative to someone who stays in one place. 10 years later, Einstein proposed his theory of general relativity. That's when we learn that time changes not only based on your speed, but also based on gravity. Back in the day, Newton thought that gravity was some magical force that makes objects attract each other. However, Einstein proposed that this isn't a force, but more like an after effect. Picture the space as some huge cloth. When you throw a heavy ball on a cloth, it curves. Now, if you throw some small balls around it, they will naturally approach the heavy ball. At the same time, massive objects like stars and planets cause space-time to curve around them. When there's something super heavy in space-time, it curves the matter around it. This curvature tells objects how to move, and this is what we call gravity. This idea created all sorts of cool predictions that later turned out to be true. Bending of light by gravity, black holes, and time dilation around these black holes, just like in Interstellar. This theory revolutionized our view on everything, but we might be on the verge of another revolution. Some philosophers have a crazy claim. They say that the things we believe about time are all just ideas in our heads, not facts of the physical world. This idea, which breaks the traditional view of time, is called the block universe. It's backed up by Einstein's theory of relativity, but extends it and makes it more complicated. Imagine the universe as a huge sandwich. This sandwich contains every moment of time, past, present, and future, all at once. Each layer or slice of the sandwich represents a different moment in time, and all these layers exist simultaneously rather than one after the other. In this model of our world, the past, present, and future are all equal. Unlike our everyday experience, where the past is gone, the future hasn't happened yet, and only the present is real, the block universe says that every point in time is just as real as every other point. Imagine your birth, this moment right now, and what you'll be doing in 10 years from now all exist together in this block. It also says there's not really a flow of time. We're used to time flowing from one moment to the next, even with Einstein's theory. But in the block universe, the feeling of time moving is more about how we experience and remember events than about how time itself works. It's like reading a magical book. All the pages exist at once, but you can only experience the story page by page. Now, this implies some scary things, like destiny, and whether free will actually exists. If everything is already laid out, does what we do matter? For example, you clicking on this video was already predetermined in the block universe. Every choice you've ever made was an illusion. You're just a program following a code, but with an ability to understand its consequences. This would explain why we order junk food at midnight, knowing that it's a bad idea that we're going to regret. But some scientists argue that time's flow and direction are as real as it gets, because cause and effect still exist. If your birth, current moment, and you in the future with gray hair all existed at the same time, you'd be able to visit your past self at any moment, and already knew what your future self is like. So this whole debate might just be about how we piece together our stories of the past, not proof that the future isn't waiting to unfold. There's also a never-ending battle between general relativity and quantum mechanics, which only adds spice to the debate. On one hand, general relativity plays with time like it's a stretchy Play-Doh. The flow of time can stretch or compress depending on the speed or gravity. On the other hand, in quantum mechanics, time isn't something that can be manipulated or changed. It's a constant stage upon which the particles and forces of the universe perform. These two fields have been fighting for a long time now, and scientists are struggling to unite them in one cohesive theory of everything. Although there are some candidates who try to merge them in a logical way, like string theory. Now, string theory sounds scary, but it's simply saying that the entire universe, with all its particles and atoms, is made up of ultra-tiny vibrating strings. Each string can vibrate in separate ways, like the strings on a guitar, and in many dimensions. The way these strings vibrate determines what type of particle they will be, like an electron or a quark. Another idea, called loop quantum gravity, says that space and time are made of tiny loops. Whether it's strings or loops, unfortunately, they would be so tiny that we simply don't have strong enough equipment to check them out yet. So until we test these theories, they can't be proven. What's interesting is that both ideas don't really need time to explain how the universe works. We think of things like tables and chairs as real, even though physics doesn't describe them directly. We say they emerge from the tiny particles that make up the universe. But with time, we're not sure how it would emerge from something else. But no matter what the answer is, you're going to be okay. If it turns out that it doesn't really exist, then it could make everything feel pointless. But think about this. We still lead our lives, and we still experience what feels like causation and make sense of everything. It still feels like it was our choice to order that junk food at midnight. So, does that being predetermined really matter? In any case, we've been wrong about plenty of things we thought were set in stone. Right now there's a big split between the block universe and our traditional theories. But we'll learn the truth over time.
Turns out we have some ways to solve the time travel paradoxes. Time travel sounds enticing, but brings with us a lot of problems. Take, for example, the famous grandfather paradox. Imagine that you travel back in time and prevent your grandparents from meeting. This alters the course of history. But how? If you erase their encounter, you cease to exist, so you couldn't even travel back in time to alter the past in the first place. There's also the bootstrap paradox. Let's say we travel back in time and give Beethoven his own compositions before he ever penned them. He gets famous for the very music you provided. But where did it originate? Did you start it? Or was it Beethoven who started it? There are many theories about time travel. One of them involves alternate timelines and parallel universes, like in Back to the Future, for example. If parallel worlds exist, we could hypothetically travel in one where the events unfolded differently, while our original timeline stays the same. This is a beautiful and paradox-free approach, but this is pure sci-fi, as we have no concrete evidence of parallel universes. So what scientists are trying to do instead is to figure out whether time travel is impossible in this one universal timeline. We've been exploring this equation for over a decade and created a fascinating concept called a closed time-like curve, or CTC. Imagine taking a path that forms a loop, bringing it back to where it started, but in time. We know that space-time is like a wobbly piece of cloth which can curve and bend when we place heavy objects on it. In some situations, like near massive objects such as stars or black holes, space-time can be curved. Now, imagine an object that's so heavy, with gravity curving the space-time so strongly that it literally loops on itself. If this idea turns out to be real, it could suggest the possibility of traveling back in time in our world line. This possibility is fascinating, but it also creates tons of problems, and scientists may have found the ways to solve them. One of the solutions is that doing paradoxical things can be simply impossible. In this scenario, we assume that the universe has some mechanisms of self-consistency. It means that while you can still travel in time, you're restricted in the actions you can take. For example, you may not be able to go back and alter your family's history, but there's nothing inherently illogical about traveling back in time to simply interact with your ancestors. In this scenario, the universe only forbids you to do logically impossible things. Scientists decided to conduct an experiment to check if it works, and the results were pretty terrifying. The experiment conducted involved the creation of a theoretical time machine. This is also called an in-principle time machine. This wasn't a physical device, but rather a quantum simulation. In the simulation, they attempted to send a photon back in time by a fraction of a second and make it interact with its past self. The goal was to find out what the photon will do. Will it destroy its previous self, avoid the interaction, or something else? What happened is that as the photon approached its past self and was getting closer to the point of creating a paradox, the experiment tended to fail more frequently. In other words, it seems like the laws of physics or the fabric of the universe might have some weird built-in mechanisms that prevent time travel paradoxes. In that case, the question is, how does the universe understand what is logically impossible? And how does it prevent us from doing these things? Which is quite scary to think about. There's another theory that the universe allows paradoxical things to happen, but also self-corrects them. Imagine a time traveler going back to stop some health condition from spreading. According to this theory, even if the traveler succeeds, this health condition would find another way to spread, avoiding the paradox. Or maybe we all exist in time loops. These loops allow objects to interact with their past selves while still maintaining a consistent timeline, because there's no beginning point. For example, trying to prevent a historical event could result in accidentally catalyzing the event we were trying to prevent. This idea challenges our understanding of classical physics and free will. But all these ideas are purely theoretical, and to test them, we first need to find the mechanism to actually travel back in time. Talking about practical time travel, we mentioned that space-time curves around very heavy objects. Does it mean that black holes can be portals to the past and the future? Maybe. Black holes are formed when a massive star collapses inward. Their gravitational pull is so intense that even light can't escape. This means they're perfect for bending not just space, but even time itself. You might remember this from Interstellar. Near a black hole, time slows down. This effect is so pronounced that a year near a black hole could translate to decades on Earth. In that case, traveling back to the past using a black hole is theoretically possible. If their gravity twists time so much that it wraps back on itself, creating a closed time-like curve, and you could enter this loop, you'd find yourself on a journey from the future to the past. But there are some problems with this. First, you can only travel into the black hole's past. Second, to enter the loop, you'd likely have to cross the event horizon, the point of no return around a black hole. To escape one, you'd have to travel faster than light, which is currently impossible. So, while black holes might hold the keys to time travel, the journey inside one might be your last. But not everyone agrees that closed time-like curves exist at all. Recent research has shed new light on this topic. The results showed that time can only move forward. The research offered a fresh perspective on how light behaves when it encounters different materials. When light moves through empty space, it travels at a constant speed of 186,000 miles per second. But when it encounters substances like water or glass, its speed can change, causing it to bend or refract. While scientists have equations to describe this behavior, they struggled with the problem of the change of the speed of light at the boundary in different mediums. Well, researchers proposed a solution to this puzzle by reconsidering how light moves through time and space. They figured out that it always remains constant as it travels through different mediums. No matter what the light encounters, it always moves forward in time. This means that light and other waves like it follow the same one-way path through time that we do. Another thing is that light also always saves its momentum, and it always stays the same, pointing forward in time. And finally, even with general relativity and with gravity bending light very strongly, it still keeps pointing forward. It can slow down to the point of feeling like time stopped, but never move backwards. This challenges our previous notions about the relationship between light and time. It implies that time has a definite direction for all waves, making it impossible to reverse. However, their equations have only been tested in one dimension, and experiments are needed to confirm if this theory holds true in reality. Stephen Hawking also disagreed with the idea of traveling back in time. He proposed a theory called the chronology protection conjecture. This idea says that the laws of physics stop time travel on large scales, even when theories like general relativity say it's possible, and that closed time-like curves simply can't exist. Hawking said that traveling back in time would mean creating new matter, which goes against the laws of physics. Although we're far from building actual time machines, if we keep diving into mathematics, we might find the truth one day.